Greetings and welcome, friends. Today we're talking about solving trigonometric equations. Yeah, we're going to combine our previously known solving skills of equations, all sorts of factoring and greatest common factor and use substitution. We're going to throw a little bit of trigonometry right in the middle of it. It's going to be amazing. But before we go there, I want to talk about this concept, principal values. Principal, right? So solutions of a trigonometric equation when a variable is restricted to two quadrants. All right, so what I'm basically saying is this. All right, sine theta, we know what quadrant sine theta is positive in, right? Of course we do. It turns out the principal values for sine are going to be the fourth and the first quadrant. All right, because I know that within that spectrum, within those angles, sine is going to experience all possible y values. Its full range will have been explored within that domain, so to speak. All right, so the principal values for sine go from negative 90 degrees is less than or equal to x is less than or equal to 90 degrees. All right. So if I ask us to solve an equation for the principal values, I'm only looking for solutions within this range, even though there's another negative value over there perhaps, or another positive value over here. But we're just considering these locations. Now cosine can't be the same principal values in those two quadrants because cosine's positive in both of those quadrants. And that wouldn't be very helpful. So cosine, they actually restrict to quadrants 1 and 2. So cosine has its principal values from 0 is less than or equal to x is less than or equal to 180 degrees. So, and then lastly, tangent. And I suppose their reciprocals would land in these quadrants as well. If I refer to the principal values of tangent, tangent will be referring to the first and the fourth quadrants, just like sine. So tangent and sine we're interested in the same values here. Less than or equal to x is less than or equal to 90. Right? So that's what I mean when I say solve for the principal values. So without further ado, I suppose let's do a problem where I solve for the principal values, I suppose would make sense. All right, so it's just a restricted quadrant answer that I'm looking for. So let's, I didn't write my little EX in a box. Of course, we gotta have that little EX in a soggy box of cardboard right there. It's never a perfect square or nothing. So it says solve for the principal values. If I've got sine x cos x minus 1/2 cos x equals 0. So by solve, I'm actually indicating that I want to know what x is equal to, not just what one of those trig functions are with respect to the first quadrant angle or something like that. So what I could do here, I'm going to use all of my knowledge in order to do this. And the first thing we can do, it turns out I can greatest common factor this. Now the fact that it's equal to 0, oftentimes I'll be able to incorporate some sort of factoring techniques to do that. So I'll rewrite this down just so it shows up a little nicer. Sine x cos x minus 1/2 cos x equals 0. What is the GCF between these two terms? What could I steal? Cos x. Now x is stuck on the inside of these, so it's not just like cos times x. Cos x is an entire part of that term. It's like a factor within it. So cos x I could actually factor out of this, and I'll get cos x times sine x minus 1/2 equals 0. Now, behold, I've got two things that multiply to be 0. Right? This is factored. And if these multiply to be 0, I know that one of them must equal 0 by the zero product property. So either cos x is equal to 0 or sine x minus a half is equal to 0. And thinking back on some of our trig thoughts, how would I solve this equation for x? Divide by cosine? No, can't do that because I got to cos inverse both sides. Also referred to as arc cosine. I don't know if some of you guys have had different math teachers maybe. They might have seen that before. So x is equal to the cosine inverse of 0. So what does cosine inverse of 0 ask? That's asking the question, for what value of x, all right, what angle is, wait a minute, my mind just blanked. Yeah, for what angle of cosine is the ratio 0? All right, when is cosine equal to 0? For what angle is that true? And I believe that occurs at 90 degrees, I believe. Right, and you could actually use your hand trick in reverse. If you go through the fingers, you'd realize when you put your pinky down that cosine is equal to 0. When the pinky's down, that's your 90-degree finger. Now question, is 90 degrees one of the principal angles for cosine? Yeah, it's right here. Right, and at that point, recall that cosine, this is cosine's the x-coordinate, and cosine is 0 there. So that works out just dandy. So let's look at this one. How do I solve this for x? Well, let's add a half to both sides. So sine x is equal to a half. And how do I get x by itself? Sine inverse, which I think is just a cool way to say it. It's sine inverse. And I get x is equal to, so sine inverse of 1/2 is asking the question, for what angles does sine equal to a half?
90.
No. 30. 30 degrees. All right. And 30 degrees, I believe, lands in one of our principal quadrants there. So my answers to this question are both 90 and 30. Okay, 90 and 30, because I was specifically looking for the principal values. All right, because technically, sine is also equal to a half at 150 degrees, right? Because sine's positive in quadrant 2, and the reference angle is 30. However, I've restricted it to just the principal values because in quadrant 2 is not in there. So that's why I'm just interested in the 30-degree one. All right. So the idea behind principal values is it just restricts our answers so we don't have a whole bunch of answers. We just got one.
Negative 330 before?
Nope, because sine is negative in that quadrant. So if it was sine inverse of negative a half, then I would have had 330 degrees or negative 30 degrees or something like that. Yep. So let's look at another one. And we've only got like 3 examples today. But they're a little bit crazy. Or as Sam would say, cray-cray. Sam's like, don't misrepresent me on the internet, please. That's not what I would say. Whoa. Look at this problem here. So, look at this. This is crazy. Now, notice it says solve for 0 is less than or equal to x is less than 2 pi. 2 pi is suggesting they ain't talking degrees, friend. These be radians. We're in radian country. Yeah, 360 degrees. Yeah. So, and also that's the other thing I want to point out is that that's referring to the full, right, 360 degree spectrum of answers. So I'll actually have more answers this time because I'm not just restricting it to the principal answers, all right, the principal solutions. Now, looking at this, I've got cos squareds, I've got cosines, I've got a constant, and I've got sine squared. Now, there's more cosines than sine, so my strategy here is I'm going to write all of these terms in in term of the same trig function. All right, write it as the same trig function. And you might realize that sine squared x plus cos squared x is equal to 1. So sine squared x is equal to 1 minus cos squared x, right? So I'm actually going to replace the sine squared x with 1 minus cos squared x using a modified Pythag. So look what I'll get. I'll get cos squared x minus cos x plus 1 is equal to 1 minus cos squared x. And now if I want to solve this, well, let's bring everybody together on one side. I'm going to set this equal to 0 and factor. I believe a lot of times these problems are factorable. So I'll subtract 1 from both sides. I'll add cos squared to both sides. Let's see, question. How many cos squareds do I have here? 2 of them. 2 cos squared x minus cos x. 1 and negative 1 cancel out, and then that all equals 0. Okay. All right, okay. So now this problem is similar to the one before it, where I'm actually going to greatest common factor this out of it. And what could I steal from both of these?
Cos x.
A cos x. Yep. So I'll have cos x times 2 cos x minus, what goes there? 1, yep, equals 0. So once again, I've got 2 things that multiply to be 0. And I can use the 0 product property. So either this guy was 0 or this guy was 0. So let's say cos x equals 0 or 2 cos x minus 1 equals 0. So the left-hand side, we know how to solve that. Cos inverse both sides. So x is equal to, so for what angle, what radians of x is cosine equal to 0? It occurs at 90 degrees. Does it happen anywhere else between 0 and 2 pi? What's cosine at 270? I think it is, yeah. So in terms of radians, that's pi over 2 or 3 pi over 2. So there's 2 answers right there for us. Now this guy over here, first thing I should do is probably get the trig function by itself. I'll just solve it all normal like. So 2 cos x equals 1. Divide both sides by 2. Cos x equals 1/2. And to get x by itself, what do? Cos inverse. And I get x equals, so all right, let's think about just the first quadrant for starters. It's positive. When is cosine equal to 1/2? 60 degrees, right? Ring finger. That's the same as pi over 3 radians. And now question, when else between 0 and 2 pi, which quadrant is cosine positive? Fourth quadrant. So in the fourth quadrant, if I have a reference angle of pi over 3, 5 pi over 3 would be the other angle. Well, let me explain it. So cosine is 1/2 at, pi over 3 right up here. And if down here, my reference angle, this is the same as negative pi over 3, or a pi over 3 reference angle, that is the same as 5 pi over 3. And the way you can figure that out is if this is 2 pi minus pi over 3, right? 2 pi is the same as 6 pi over 3. Minus 1 pi over 3 would be 5 pi over 3. All right, so it's just all back to our reference angle work there. This actually ends up having 4 solutions to it because they wanted solutions between 0 and 2 pi. Right, and oftentimes that can be the case.
How did you figure out? Sorry, you went from like over here, you went cosine inverse, and then how did you figure out the cosine inverse of 0?
Well, when is cosine equal to 0? That happens at 90 degrees, which is pi over 2.
Okay.
All right. Let's see. Yeah. So cosine is 0 here, and cosine is 0 here. Right? Is the idea. So at either of those locations. So this is pi over 2, and this is 3 pi over 2. Is the idea. So let's do one more example. And this is going to be everybody's favorite. Would it be appropriate for me to call it your fei-fei? Is that a lingo, a terminology that's used? I'm unsure, guys. Yeah, this will be your fei-fei. Fei-fei sounds like some sort of nickname for a grandmother. Like you'd call her your fei-fei. I don't know. I don't know. Like your Nana, your Mimi, your, I don't know, your Moo, your Fei-Fei. I don't know, I could see that. All right, this problem, what is going on with this? There's a tan to the 4th. What? This problem is going to take up a full page, yeah. Roughly. Don't worry, you can always go on to the next page. Now, let's use the same technique we had earlier. Let's rewrite these all as one trig function. All right. How do I relate secant and tangent? I think there's a Pythag identity that does that. Tan tan squared x plus 1 is equal to secant squared x. And I guess I could probably do this if I rewrote tangent in terms of secant, but I'm going to just replace the secant in terms of tangent. I think it would make more sense. So I believe we could just substitute the secant x, no, secant squared x, the whole thing, yeah, and plug this in there. Also, oh, notice the directions. Solve for all real values of x. So that doesn't mean just between 0 and 108, or 0 and 360, or just the principal angles. That's like all possible angles, including like any and every of the infinitely many coterminal angles. All right.
Isn't that like a lot?
Yeah, that's a lot. Infinity, most people would agree infinity's pretty big. Pretty big. So let's see. Let's replace secant squared with tan squared x plus 1. Okay. So let's do some distributing and simplifying here. Distributing. So I'll get 2 tan squared x plus 2 minus tan to the 4th x. And I actually anticipate that, well, I'm seeing like multiple exponent things going on here. I'm thinking we're going to have to factor this again, which I suppose we've done on every problem so far. So I'm going to also simultaneously move this plus 1 to the other side. All right, just to set it equal to 0. And I might as well try to write this in standard form from highest exponent to lowest. So let's rearrange this. We'll write this as negative tan to the 4th x plus 2 tan squared x. And then it looks like plus 2 and plus 1. Those are buddies. Those are friendly friends. That's plus 3. Now, I don't like starting off with a negative. So whether you think of this as dividing both sides by a negative or multiplying both sides by -1 or just changing everybody's sign, let's just change everybody's sign. So that'd be -2 tan squared x -3 equals 0. And this is where I can't do my regular old GCF trick because I've got this third term in the way. Oh, man. However, what if we could imagine this problem was different? What if I could imagine it was something squared minus 2 times something minus 3 equals 0? What would have to go in those parentheses? Yeah, tan squared x, right? Man, why are like my tans just like gross looking? Tan squared x in both of them, right? So do you guys agree that tan squared squared is tan fourth x? Right, okay, that seems to make sense. So we're going to do this thing called U substitution, where I'm going to pretend like, let's just make up our own variable. Let's just say U r tan squared x, right? And I'll rewrite this in terms of U. Yeah. And I can now solve this in terms of U, and then I'll get x back into this situation later, right? We'll just pretend this problem was easier. And we'll work in our imaginary universe for a little bit here. So to solve this quadratic, fortunately I don't have to AC method because the leading coefficient is 1. But I can solve this, find the factors of 3, which are 1 and 3. Which of those subtract to be 2? Well, the only ones that we have here. Which, by the way, if this was not factorable, you could still solve using quadratic formula or by completing the square. Which, fortunately, I think all of tonight's problems are factorable. So you're welcome. You're welcome, guys. So I'll have a u with a 1 and a u with a 3. What are the signs going to be? Let's see. It's probably been a while since we... They got to be different signs because they multiply to be negative, and they have to add to be a negative, so the 3's got to be more influential as the -1 is 1 and -3.
Mr. Waddy, if I take column Lazito away from this.
That's fine. Yeah. Go for it. All right, here's checking out some...
I did you a favor.
Yeah, I like that. I like that. So now I've got the product of two factors equals 0, so therefore either of those are equal to 0. And I solve them. You see, friends, solve them. And I get u equals -1, or ur. Is that more proper? ur3. I like it. However, if you solve this problem and someone's like, tell me what x is, and you're like, u is -1. And like, they're just like, what are you talking about? There was no u in the original problem. Like, you're a crazy person, right? That's what they would think. So I've got to bring this back into context for x, right? Because like there was no u in the problem. This is crazy. This is crazy, guys. So let's plug this u in here. Let's plug it into both of those. Bring this back in terms of tangents and x's. So tan squared x is equal to -1, or tan squared x is equal to 3. Interesante. So tan squared x, how do I get tan x by itself? How do I get rid of the square? Root both sides, plus or minus, don't forget it. Hey, it's the same step over here. Oh, yeah, on this left-hand side, I'm going to get tan x is equal to plus or minus I. And I don't know about you guys, but like, if you try to tan inverse that.
We don't need to, because it only needs real values.
Oh.
Well,
Nice.
yeah, when is tangent ever equal to I? For what angle? It never was. The answer to this is just no. Like, I'm not doing that. Like, forget you. But I'll do this problem over here. I can do that. So let's see. Tan x tanks is equal to positive square root of 3. Over here, tanks is equal to negative square root of 3. And how do I get rid of the tans? Tan inverse. You can call it tan verse. I know you think it'd be so cool if you did. It's fine. Tan verse. That looks like ta. There we go. Tan. So I'm going to get x equals. All right, question. It didn't specify radians or degrees on this problem, I don't believe. Whoa, I just did a zoom there. That's fine. So I'll let us work in degrees here. How about? Because I'm a nice guy. For what values is tangent the square root of 3? Yeah, ring finger, guys, right? Square root of fingers to the left divided by the square root of fingers to the right.
Got it.
Yeah, tangent is equal to the square root of 3 at 60 degrees. Okay, where else within 360 would tangent equal positive square root of 3?
240.
240? Yeah, tangent's positive in quadrant 3. Sure. I like it. Okay, and I guess we end up picking up the rest of them here anyway. When is tangent equal to negative square root of 3? Well, it's going to have a 60-degree reference angle.
150.
Nope, 120. So 180 minus a 60-degree reference angle is that. And then 360 minus a 60-degree reference angle is 300. Now, I don't know if you guys realize this, but these are some real numbers. But these are not all real values of x that make this equation true. So yeah, we've got to kind of bring this into context. Let's rewrite these as the coterminal versions of these angles. All right. So I'm saying that x is equal to 60 plus all 360n.
Because 60 and add another circle to it, and that's how.
Right, coterminal, add any number of full circles to that, that's another coterminal. Or subtract any number of revolutions, and you'll still land on that, right? Okay, so that's some of my answers, infinitely many of them. Or it's equal to 240 plus 360n. Or it's equal to 120 plus 360n. Or it's equal to, my goodness, 300 plus 360n. And I believe it's actually possible to simplify this. These two expressions on the left, how far away is 60 degrees and 240 from one another? 180, yeah. It turns out I can actually rewrite that as x equals 60 plus 180n. All right, just to kind of draw a picture of that so you see what's going on. Right, 60 degrees is here, 240 is right here, and I said like this angle works or any number of 360s plus that, and then I said this angle works plus any number of 360s plus that, and I realized, well, maybe I could just simplify that because 180 would bring me there, another 180 would bring me there, another 180 would bring me there, so I just can kind of like simplify that, you know, and it turns out this can be simplified as well to 120 plus these happen to also be 180 degrees apart. So we might as well simplify them while we can. And we've just found all possible values, all the real ones that would work for x in degrees for this original function. So just to show you, look at all this work we just had. I like it. Good stuff. Actually, sometimes I like to just zoom out and admire all of our beautiful notes. Look at those colors. Thing of beauty there. Yeah. So just so you kind of get the overall context, I replaced everything in terms of the same trig function, and then I right? Factored it, U substitution, blah, blah, blah. And then I had to, like, I eliminated this guy because it was imaginary, and then I found both of those solutions. And then I had to find the coterminal ones because I was looking for all reals. And then I was able to simplify those a little bit. So, all right. Whew. Thanks for watching, Internet friends. Have a great day. Bye-bye.